Hello everyone, Professor Dustin here, and this video is going to be about statics. So statics is a particular kind of physical problem in which the objects in question are at rest. So specifically what we care about is that the acceleration is zero, but it's very often that in these problems we also have that the speed is zero. So the reason the acceleration is zero is significant in statics problems, rather obviously, is because then the force, the sum of the forces, is also going to be zero instead of m times a. So we already know a fair amount about those kinds of problems. For instance, let's say we have a block sitting on the ground, and I'm pushing at this block, on this block with a force F. Well, I can draw a free body diagram of that block. F, gravitational force downwards, normal force upwards. And of course what I've done is I've replaced this block, which is like a real object, with a point to represent the location of the center of mass of the block. Well, if this is a static situation, if I say the acceleration is zero for this block, that means the sum of the forces must be zero, which does not seem to be the case for the block that I drew. So clearly there is some other force acting in the horizontal direction. Maybe it's the force of friction. And now the sum of the forces on this block are zero. So by saying that we had definitely a static situation, I knew that there was some force of friction. Okay, so that's essentially statics for the case of Newton's second law for an object which has some motion of its center of mass. This tells me that the center of mass is not moving. But of course, that only works for objects which we can replace by points. What if we really wanted to consider what would happen if this force was acting in a different location on the block, right? You can imagine that the force was acting at the top of the block, and I pushed hard enough, maybe the block would tip over, it would rotate. This does not take into consideration anything about extended objects or rotation. But for a static situation, we want the objects to not only be not moving in the x and y directions, but also not rotating. So let's get an example of an object which could be rotating. So here's a beam. And let's attach a let's attach a rope to about the center of the beam. So that's about the center of mass. And then I'm going to put two masses on either side of this beam, M1 and M2. Now, if this rope is attached to the center and it's like infinitely strong or something, then no matter what I do to the beam, the center of mass is not going to move because the rope is just going to be strong enough to hold the beam up no matter what. So this is true for this beam. But on the other hand, the two masses, if they're different, could make this beam rotate in some complicated way. But if we want to consider a static situation, we want to consider when that does not happen. So it turns out that this is not enough information. We need to do something a little bit different over here. Specifically, we need first a tool which allows us to put the forces in different places on the object. That's often called a torque free body diagram. Generally, I just call them object diagrams and add the forces in their specific locations. So in this case, what I'm going to do is I'm just going to redraw the beam with the forces acting in the specific locations the forces are acting. So the tension is acting in the center. The gravitational force from the first mass is pointed downwards, and the gravitational force from the second mass is also pointed downwards. So that's like maybe a torque diagram or something, but it shows the forces in the specific locations. So how do we know if this object is actually not rotating, that is actually satisfying the condition of static equilibrium? Well, I've already said the word torque, and recall that is how you tell if something is rotating, is if you check what the torque acting on that object is. So recall that the definition of the torque is a vector. As an equation, it is r cross f, where r is the vector from the location wherever you're considering the torque to be around. So you have to pick an origin. Typically, we pick the center of mass, and that's what I'm going to do in this case. The distance where the force is acting is called r. And then you take this cross product, and you can find out what the torque is that way. And you can see that this torque, meaning this force, is going to make this object rotate in that sense. Now, remember that normally we don't consider these torques as vectors. We often will write them as magnitudes, RF sine phi, where we have to make sure that in order to get that, that angle correct, that R and F are arranged in this particular way, and that angle is exactly that angle. Remember, if they're not arranged this way, we have to move them around until they are. So we get the magnitude of the torque that way, and then we can get the direction of the torque by just doing the right-hand rule. Okay, so we know over here that the condition for static equilibrium for an object which can be replaced by a point is this. The sum of all the forces is 0. Well, we want a similar equation, but for the case of torques and rotation. So we know when an object is also not rotating. It turns out that's actually very easy because it's just the rotational version of Newton's second law. So it turns out that all we need to do is ensure that the sum of all the torques acting on that beam or that object is going to be 0. So each one of these forces is going to contribute a torque, sum them all up. If they equal 0, this object is in rotational equilibrium. It is not rotating. Okay, so let's talk a little bit about the directions here, right? So if we are doing a typical physics problem, we often have forces and positions which are just in the plane of the board, in just the x and y direction. So in that case, we have an equation for the force in the x direction, and we have an equation for the force in the y direction. So we want to consider what happens to the torque and the direction of the torque in these kind of typical problems in which the force and the position are just in the plane of the board. So let's figure out the direction for the forces that I have here. So first let's start with this force here acting with a displacement vector between the point of rotation and the application of the force that R. So remember the right-hand rule. Take your right hand, point it in the direction of R first, then curl it in the direction of F. I can't curl that way. F is pointed downwards, so I have to flip my hand around. Then it curls downwards. Then I get into the board. So into the board, we usually indicate as little x like that, as if it's a vector arrow going away from you, okay? But it's pointed into the board. Let's do the same thing over here. There's that vector which shows how far away from the point of rotation that force is acting. My right hand, go like that. I can curl my hand downwards like that. I get out of the board. And typically the way that we denote out of the board is with a little dot like that. So it looks like the arrow is coming out towards you. We can also do this for the tension. If we do the tension from the same point, because whenever you calculate the torques, you have to calculate them about the same point, or it doesn't. The calculation doesn't make any sense. About this point, this tension is acting at that point, so the distance between the point of application and the point of rotation is 0, and so the torque due to that thing is 0. So this is not contributing a torque and not making this beam rotate. That makes a fair amount of sense. It's attached there, so it wouldn't rotate there. That's the point about which it is rotating. Okay, so we have one more force here, so let's also figure out the torque. On this particular case, we have R going this way, F going this way, out of the board. So another little dot with an arrow. So in all these cases, F and R were in the plane of the board, but the torque was out of the plane of the board. That's not a coincidence. That's because in this cross product, the result of the cross product is perpendicular to both of the vectors that go in. So perpendicular to R and perpendicular to F. The only way that can happen is if R and F are in the plane of the board and the torque is out of the plane of the board. That is in the Z direction. So as long as we're staying in these two-dimensional motion cases, all of our torques are only going to be in the Z direction, and we only have to add one more equation to our considerations for static equilibrium. So this set of equations, which is 3, sum of the forces in the x direction is 0, sum of the forces in the y direction is 0, sum of the torques in the z direction is 0. That is going to be the complete set of equations for our generic case of static equilibrium. Now, if you have a more complicated situation where you have forces acting in the x, y, and z directions, then when you take those various cross products, you get torques which could also be acting in the x, y, and z direction. So in the general case of three-dimensional forces, you get three-dimensional torques, and you have 6 total equations, and then the considerations become much more complicated. We are generally not going to deal with that. Mostly our problems of static equilibrium will be 2 equations for force, x and y, and 1 equation for the torque in the z direction, and you need to find the torque in the z direction by doing these kinds of things, making sure you know how far away each force is acting from the point of rotation, plugging into this equation, and then making sure you understand whether the torques are making the object rotate clockwise or rotate counterclockwise. Add those up to be 0, and that tells you the condition of static equilibrium. All right, great. So that has been an introduction to statics. Next thing to do is to go on and practice some of these problems, which is what we're going to be doing on the homework and in class. Great. Thank you guys for watching, and I will see you shortly.